If you have ever stared at a string and thought, I could fix this if I could just change a few letters, that's the exact power you get here. A string and one rule. Change up to k characters into anything you want. The question is, how long a streak of the exact same letter can you actually build? Look at this. AABABBA. K equals 1. 1 swap. Turn that B into an A and you have got 4 A's in a row. Longest valid length is 4. Longest repeating character replacement. LeetCode 424. Variable window, max frequency trick. 1 inequality. Let's get into it. Formally, given a string and an integer k, you can replace up to k characters with anything. Find the longest substring that can become all the same character. Two examples. ABAB with k equals 2. Swap both b's, get AAAA. Output 4. AABABBA with k equals 1. Replace one b inside the window AABA. Get AAAA. Output 4 again. And here is the shift that makes this solvable. We never need to know which characters get replaced, only how many. That one idea is what makes this solvable in a single pass. Constraints: string up to 100,000 characters, uppercase only. That's all those numbers are doing. Before we jump into the approach, let's quickly place this in the series. Looking at this problem, you might wonder, is sliding window even the right tool here? The question looks completely different from anything we have done so far. It is still sliding window, but episode 7 uses it differently from every previous episode. In episode 5 and 6, we had a fixed window size, checking against an exact frequency match. Episode 5 returns true or false. Episode 6 collects every matching position. Episode 7 has no fixed size, no fixed target. Instead, we ask, can this window be fixed with at most k replacements? That one question is the new move, and it gives us a completely different validity check, which we will define right now. Here is the rule, and it's the whole video. Window size minus max frequency less than or equal to k. Think of it like an election inside the window. Whichever character has the most frequency or votes wins. You don't need everyone to agree. You just need the number of disagreeers to be k or fewer so you can replace them all. Watch it work. Window AABA, length 4. Most frequent is A. This is with 3 votes. 4 minus 3 is 1 disagreeer. K is 1, so we can afford that. Valid. So we keep R moving. Window keeps growing. Now extend to AABAB. Length 5. A still has 3 votes. 5 minus 3 is 2 disagreeers. More than K. We cannot replace 2 characters with only 1 K. So this window is invalid. We move L forward by 1. Drop that leftmost character and shrink the window by 1 step. Now we are at ABAB, length 4. Max frequency is still 3. We never decreased it when we shrank. Check. 4 minus 3 equals 1. Valid, we stop shrinking here. So valid, we keep growing the window. Invalid, we shrink from the left. That's the entire algorithm. Let's now trace this across the whole string step by step. Full trace. Watch L and R below the string and the window column on the right as we go. R starts at index 0. Character A enters the window. Count of A is 1. Max frequency is 1. Window size is 1. Formula 1 minus 1 equals 0, which is less than or equal to K. So valid, grow. R moves to index 1. Another A enters. Count of A is 2. Max frequency is 2. Window size is 2. Formula 2 minus 2 equals 0. Valid. Grow. R moves to index 2. B enters. Count of A is 2. Count of B is 1. Max frequency stays at 2. A is still the leader. Window size is 3. Formula 3 minus 2 equals 1. Exactly K. So valid. Grow. R moves to index 3. A enters. Count of A is now 3. B count is 1. Max frequency jumps to 3. Window size 4. Formula is 4 minus 3 equals 1. Exactly K. Valid. Grow. Base size so far is 4. Window AABA. This is the window we want to protect. Now R hits index 4 and this is where the rule breaks for the first time. R moves to index 4. B enters. Window tries to grow to AABAB. Size 5. Check. 5 minus 3 equals 2 more than K. This is invalid. So shrink. Drop A at index 0. L moves to index 1. Window is now ABAB. Size 4. Check again. Max frequency is still 3. It didn't decrease when we shrank, even though S real count is now 2. That is the stale max frequency. So formula with stale value is 4 minus 3 equals 1. This is valid. Grow. We will come back to why we have not updated max frequency and why this is still stale. Keep watching. Now base stays at 4. Window ABAB. R moves to index 5. B enters. Window tries size 5. Formula breaks again. Shrink once. Drop A at index 1. L moves to index 2. Window is now BABB. Size 4. Max frequency unchanged at 3. Formula 4 minus 3 equals 1. Valid. Base stays at 4. R moves to index 6. A enters. Window tries size 5. Breaks again. Shrink. Drop B at index 2. L moves to index 3. Window is now ABBA. Size 4. Max frequency unchanged at 3. Formula is 4 minus 3 equals 1. Valid. End of string. Best size we ever saw is 4. That's our answer. Now let's formalize those 5 moves. So here are the 5 moves. 1. As R moves right, update the count for that character. Update max frequency if this character's count is a new high. 2. Check the rule. If window length minus max frequency is greater than K, the window needs more replacements than we have. It's invalid. 3. If invalid, move L forward by 1 and decrement the count of that character we just dropped. We only shrink by 1 step per iteration, not a full loop, just one move. 4. After every single step, update max length. It's the biggest window size we have ever seen. 5. Once R has scanned the full string, return max length. Time complexity is O of n, 1 pass. Space complexity is O of 1 because the alphabet is fixed. Uppercase English only. So the frequency map holds at most 26 entries, no matter how long the string is. Now, about max frequency never going down, this one trips people up. When we shrink, we decrement the count of the dropped character. We never touch max frequency. So after a shrink, max frequency can be higher than any actual character count left in the window. It's stale. Here is a concrete example. When our window was AABA, A had count 3. So max frequency became 3 and max length became 4. Then we added B. The window grew to AABAB. The rule broke and we shrank dropped that leading A. Now A's real count is 2, but max frequency is still 3. So the window ABAB gets checked as 4 minus 3 equals 1, valid. But the real check would be 4 minus 2 equals 2, actually invalid. We are keeping a window we technically should not. Here is why that does not cause a wrong answer. Max length is already 4 from the legitimate AABA window. ABAB being wrongly kept does not change max length. It stays at 4. The window just slides forward at the same size. We never record a length that was not genuinely achieved. The correct answer is already safely stored before the staleness ever kicked in. Here is what all of this looks like in actual code. 4 moves mapped to code, one block at a time. Setup. Count dictionary to track how many of each character are currently in the window. Left pointer at 0, that's the left edge of the window. Max frequency at 0, that's the highest character count we have ever seen inside any window. Max length at 0, that's the longest valid window we have ever seen. Grow. For every right pointer, we pull the character at that index. Bump its count in the dictionary, then check, is this character's count now higher than max frequency? If yes, update max frequency. This is why max frequency only ever goes up. We update it when a count rises, but we never touch it when a count falls. Shrink. Compute window length as right minus left plus 1. If window length minus max frequency is greater than k, the window has too many characters that are not in the majority. We cannot fix it with what we have got. So we drop the leftmost character, decrement its count, move left forward, just one step. Track best. After every iteration, whether we shrank or not, we check is the current window the biggest we have ever seen. Max length is updated every single step, not just the window which is valid, because even after a shrink, right minus left plus 1 tells us the current window size. Loop ends. Return max length. That's it. Let's run this on LeetCode and see it pass. Same code, straight into LeetCode. 4 to 4, longest repeating character replacement. Problem is already familiar. Let's just build it. This is my frequency map. Left is at 0. This is my left edge. And max frequency and max length is set to 0. This is tracking the highest frequency seen and the longest window seen so far. Now we will iterate through the whole string. R is expanding right on every iteration. We will get the right index now. Now we will bump its count. Then max frequency, which is max of max frequency and count of ch. This line only ever goes up, never decreases. Now window length is right minus left plus 1. So if window length minus max frequency is greater than k, rule breaks. So we will drop the left character and move left forward one step. Now we will get the best window we have ever seen, updated at every step. Notice one thing here. Here I have used right minus left plus 1, not window length. Because when we are shrinking, at that time left is already incremented by 1. So if we will be using window length instead of right minus left plus 1, this will be using a wrong left value. So the max length will be maximum between max length and using the updated left right minus left plus 1. Now return the max length. Let's run the code. All test cases pass. Let's submit. It submitted successfully. This is one pass, exactly the way we built it. Now let's check the edge cases before we call it done. 4 edge cases to know. K, at least the string length. You can replace every character. so the whole string becomes uniform. Output is the full string length. K equals 0, no replacements at all. The window stays valid only while every character inside it is already the same. Answer is the longest run that's already uniform. All same character. Max frequency equals the window length at every step. Window minus max frequency is always 0, always valid. Window grows all the way to the full string. And the one that actually causes bugs. Window minus max frequency landing exactly on K. The validity rule is less than or equal to K. So equal to K still passes. The window is valid. Keep growing. The bug people write is putting greater than or equal to K in the string condition, meaning they shrink even when window minus max frequency equals K. That throws away a perfectly valid window. The correct code is strictly greater than K only for string condition. Equal to K, you have exactly enough replacements. Don't shrink. With those covered, here is the 4 things to carry out of this episode. 4 things to carry. Variable window grows freely with R. Only shrinks when the rule breaks. The rule: window length minus max frequency less than or equal to K. One inequality. That's the entire validity check. Max frequency never decreases. Even if it's still after a shrink, the final answer is still correct. And you are tracking the longest length ever seen, not which window achieved it, not the final window position, just the length. That validity rule is exactly the condition you will write when you implement this yourself. And here is where this technique sits inside the full pattern family. Here is the whole pattern family laid out. Longest substring without repeats. Variable window, validity check is 0 duplicate characters. Minimum window substring. Variable window, validity check is the window contains all required characters from T. Shrink until it stops being valid. Permutation in string. Fixed window, validity check is frequency map matches exactly. Return true if any window matches. Find all anagrams. Same fixed window, same exact frequency match, but collect every position where it matches, not just the first. And today, variable window validity check is window minus max frequency less than or equal to K. 1004 next. Same variable window, but the validity check becomes at most K zeros in the window instead of K replacements. The structure is identical. Same family, different validity check each time. That's the pattern. 7 episodes in. Basic window concept, fixed size, variable size, minimum window, permutation check, collecting all anagrams, and now max frequency replacement. Episode 7 done. One more pattern before we wrap the series. Next up, max consecutive ones 3. LeetCode 1004. Variable window, K flips instead of K replacements. After that, we close the series with a full practice set covering all 3 window templates. If you have made it this far through the series, episode 8 is the one where everything clicks together. Quick recap. Variable window, grow with R, shrink only when the rule breaks. The rule is window length minus max frequency less than or equal to K. Track the best length you have ever seen, not the final window. Still max frequency is fine. If this helped, a like goes a long way. Subscribe for the rest of the series and drop your questions below. See you in episode 8.